about network layer APIs, which I think builds on top of a lot of this architecture that MEF's putting into place. So with this, for those of you who were in the tutorial the other day, I'll briefly touch on some of the subjects that I hit there. First of all, what is SDN? And then taking a look at what is network programmability and what are kind of the things that we're able to do with network programmability, why is it important, and how does it work? Then to take a look at network programmability beyond what most people think of it as when you think of programming an individual device and moving more to network layer APIs. And then wrapping up with some conclusions. So first of all, what is SDN? So when SDN really first came on the scene, what the main things that people thought about, well, first of all, there was the OpenFlow protocol that was defined as a new way of signaling between this control plane and a data plane, and as opposed to having those both co-resident and mingled together within your router or switch, you were actually going to physically separate them. And the protocol that you would use to talk from one to the other was OpenFlow. So those came onto the scene, and the idea being that you could centralize the control. Once you had broken it out, it didn't need to be distributed across all these different boxes, so you could centralize the control plane. And then for your data plane, rather than having to have real expensive hardware, dedicated hardware for that, you could actually make use of white label switches and just have them take care of all of that for you. And I'd say that's a valid use case, and we've seen people working on that and deploying that with some success. But really, to me, the true value that came around with SDN was this idea of being able to programmatically interact with the network. There's a lot of data, a lot of valuable data that's in the network, in the data plane, and if you're able to expose that to applications that are riding on top of it, and to do that programmatically so that you can look at it and make changes in real time, that's where I think the true value is. And so I'd really say that, to me, network programmability is the most valuable thing that's come out of SDN. Looking at that pictorially, have just a network stack here, I guess. And you can see the separation of the control plane and the forwarding plane. But again, the real value here is if you dig all the way down into the bottom of the network and where all the packets are really flowing, and you're able to make that information that the network has available programmatically to an application, to the application layer up above. There's a lot you can do with that information at the application level to then figure out what's wrong with the network, or how can I make the network work better? How could I reprogram it so that it could work better for my intended use, for my applications? And then you can optimize the experience that way. And so creating this closed loop system that's not based by someone going in and observing and making changes over the course of, say, days, weeks, or whatever, but actually programmatically happening at real time. That, to me, is the real power and possibility that SDN unleashes for us. So with that vision in mind, if you talk about an SDN controller that is going to be used in this type of network, what is it that you need from it? And I would say, of course, it needs to be able to control your network and interface with it. But the other really key thing is that it needs to be a platform on which you can create and run these applications, these network-aware applications that are making use of these interfaces. In order for that to be quick and easy for you to do, you need to also provide APIs, and not just any API, but developer-friendly APIs that really lower the barrier to entry here to start taking advantage of some of these capabilities. And at the same time, you don't want to have to worry. You don't want the application developer to have to worry about the nuances of the network and the protocols that are being used on the network. Rather, you want to be able to abstract that away. And so these are key things of an SDN controller. As an example of an SDN controller that I think does this very, very well, OpenDaylight is an open source SDN controller. It's been around, I think started in 2014, and provides a lot of this functionality. What you see here on the screen right now is in the middle, those are all the network services that are just kind of any SDN, any network controller, I would say, is going to have to provide for you. And then down at the bottom are just different types of network elements. And I purposely chose these ones where on the left-hand side, you see OpenFlow-based. These could be those white box switches that I mentioned before. OpenDaylight can control those very well, but it can also control these other types of switches, which you may have been using your network before SDN really came about, or which you may have reason for using for some other reason. Could be virtualized routers and switches, could be physical boxes. So now I'm going to show how all that can work. So fortunately, OpenDaylight has the ability to talk not just OpenFlow and the different versions of OpenFlow. You can see that on the far left-hand side, but also all these other different networking protocols. Things like BGP and PSEP, which have been around and well used in the network for years and years. And also some newer protocols, which I'll talk about later on in the network programmability space, like RESTCONF and NETCONF. So what that does is it allows OpenDaylight to control these different network elements that may be in your network. Now, super critical here is that there's also this MDSAL, as it's called within OpenDaylight. That's your model-driven service abstraction layer. And what that does is abstracts away the details of the underlying network, the different devices, and the different network protocols that are being used, and allows you to present a view up to applications above, which is available to them through this API layer that OpenDaylight provides. And you'll see there, if you're familiar with APIs, common things that are used in the industry. RESTCONF and NETCONF, which are two, I'd say, network-specific protocols that have APIs behind them. And then also just REST-based APIs in general can be defined and added to OpenDaylight. And it can make to provide access to information about the network and the network services that are running. So now let's take a look at network programmability. So the first thing is to understand why network programmability is a big deal. And the main driver for it is cost, speed and cost. So if you look at the cost of your network, sure, the equipment, the actual routers, switches, controllers, all that tends to be fairly expensive equipment. Even with the bringing in white box label switches, there's still cost to that. However, that CapEx cost is actually the smaller bit. The larger bit is the OpEx, what it costs you to manage and run your network. Right? That's where the majority of the time and effort is spent, and that's where when you want to turn up a new service, the amount of time that you spend to add the compute power that you need is really quick and easy, especially with, say, cloud-based compute that we have today. But the networking aspects of that, whether it be on-premise or cloud, that tends to be more complex. That tends to take more time. So network programmability, what we're really doing here is enabling you to bring down these network costs and to get those sort of similar fast deployment times that you're able to get in the compute space with the networking space. So I guess back in the 1990s, we had a protocol defined called SNMP, Simple Network Management Protocol, which sounds like it actually enables network programmability. To some extent it did, because it allowed you to monitor devices and to get real-time faults from them. But it really, and is quite good at doing that, I'd say it more or less failed in terms of providing the ability to configure your network and to make changes. And really no one's using SNMP back then or now to configure their networks. Instead, what everyone does is relies on the CLI and CLI scripting and get pretty clever with this to sort of automate some things, but it's very brittle because you need to work with every single vendor's individual CLI. You need to do a lot of regex, pattern matching to find the things that you want. And those interfaces were meant for humans to use at a keyboard as opposed to computers to use programmatically. So really, network operators came to the IETF, which is where a lot of these networking standards were developed, and said, hey, you gave us SNMP, but that's not quite meeting our needs. We need something better. We're really struggling to maintain and monitor and configure all these devices and run our networks. So what came out of that was, the things that we had learned about SNMP, what it worked well for and what it didn't, how people were using vendor-defined CLIs and interacting with the equipment, the types of use cases that they were addressing and how they addressed them. And then the overall requirements of the operators, where even with SNMP and with what they were able to do with the CLI, where were their pain points? And what came out of that was defining some new specifications in this space. NETCONF and RESTCONF, which are two network management protocols that were defined, and very importantly, YANG, which is a protocol for modeling network data. So we'll take a quick look at each of those. So YANG, as I mentioned, it's a data modeling language. It could be used for other types of data, but it was specifically defined for network data. Defined by RFC 6020. The key things that YANG really aimed to do was to put some semantics behind what the network data was, to put constraints behind it, to take things that we got used to from the programming space, like predefined types and reusable types, and to apply those to how we would define network data, as opposed to it just being something that was defined by the way the CLI happened to work. So really what this did was it took the way that you define a network element, like say a router or a switch, its configuration, and makes it, puts a contract language behind it that captures all the syntax and all the semantics of it. And what that does then is it makes it much easier for you to interact with it programmatically, as opposed to the ways you would have had to have done with your CLI scripting. Just a quick example of what a YANG model looks like. It's a text-based I guess YANG models are text-based is what I wanted to say. And it's really not that complicated. Basically, you have the idea of you have containers, and a container is the top-level element that will define your YANG module. And then within a container, that's just a grouping mechanism. And so you could actually have containers nested within containers. Containers can contain lists, and those lists would, in this example, it's a list of network topologies. So then we'll have a full list of all the different network topologies in your network. And where something like NETCONF topology could be one, you could have other topologies as well. I'm not going to spend too much time on that now, but we'll look at them at YANG models in a little bit more detail later on. Instead, I want to talk about NETCONF. And so if we have a way of defining the data, right, that's what YANG is providing. Now we need a way to interact with the device using that definition of the data. And that's what NETCONF was defined for, Network Management Protocol. So NETCONF was defined initially in RFC 4741, and that was actually before YANG. So the idea was it said that we'll give you some operations to interact with your network devices, and you, the vendor, can define your model for how your data looks. So the problem was that every vendor went off and came up with their own model, which was basically modeled after their CLI. And so it was a little bit better because you could programmatically interact with it better, but it was still different from one vendor to another, and even from one model of a vendor's equipment to another one. So it wasn't quite what we needed. Fortunately, with YANG, we got the ability, a standard ability for defining, for doing this data modeling. So then NetConf was updated to take advantage of Yang, and that's why if you look for NetConf RFCs today, you'll see 6241. The way NetConf works, it runs over SSH. The data, the payload, which is essentially defined by your Yang model, is encoded in XML. And very important to NetConf is that it provided the ability for you to have different data stores. Things like your running data store, you have operational data stores. This ability to distinguish between operational data and the actual configuration data is very important and key to NetConf, and it provides that capability. Also very important is the ability to make multiple changes and to perform that change as a transaction, as opposed to having to do things individually. If you've ever, like if you've been using the CLI on a piece of network equipment, you typically want to change multiple things and then be able to apply it. And if there's something invalid with that configuration, you want to be able to roll back. Those types of mechanisms are built into NetConf as well, and they were completely missed with SNMP. So really NetConf, what it does is it provides those fundamental building blocks that you need in order to programmatically interact with the network. Just to give you a little bit closer idea of how it works, I mentioned it runs over SSH or TLS. Almost everyone I've seen is using SSH. So you can imagine the way this would work is you could have your client application, which would essentially establish an SSH connection to your router or switch. When you do that, there's a hello exchange that happens, in which case you learn all of the Yang models that are supported by that network device. And now once you know those Yang models, you know all the APIs that you can use to interact with that device and how you can look at all of its configuration, how you can change all of its configuration. And so you can go and manipulate the way those that data store looks, and then when you're done, you can just go ahead and close the connection. So that's great. We can now interact with our device, and we do so based on these standard models. So life is getting pretty good. However, if you look at a lot of the developers today and what they're doing, we have a lot of web application developers. And they've gotten very comfortable and proficient with using REST-based APIs. And there's a huge suite of tools which are out there for these REST-based APIs. So this whole thing with NetConf was kind of getting bypassed by a lot of them. Your network engineers were still using it, but there's a whole huge portion of the developer community which was more or less going, that doesn't look like anything I know, and not really taking advantage of these capabilities. So realizing that, another protocol was developed, RESTCONF. And what that's basically doing is taking the capabilities that I showed with NetConf, but mapping them onto a RESTful API so that you can take advantage of all these same capabilities, but using the RESTful verbs like get, put, post, and HTTP style request. So instead of running over SSH, it runs over HTTP. Instead of saying that the data needs to be encoded using XML, as we did with NetConf, you also have the ability to use JSON, something which is much more kind of intuitive and well supported by tool chains and languages such as Python, which are what a lot of developers today are using. So really nothing new, but rather a different way of interacting with a network is provided by RESTCONF and the ability to take advantage of REST APIs and JSON. Just to show you quickly what that looks like, if I have a couple, on the left-hand side, I have a couple different Yang models, and then on the right-hand side, showing you how you would build out your HTTP request that corresponds to what you interacting with that Yang model. So as you look at different components of this URL, basically the first part is what's the server you're talking to and what port is it listening on. Then the fact that you're using RESTCONF. And then the rest of it starts to flow from these Yang models. So you can see the network topology, well, that's the Yang model that I want to interact with. And within that Yang model, I want to interact with the network topology. Now, the fact that it's the config data store that I'm working with, that's denoted by the RW there, read-write, as opposed to RRO, which you see further down in that same Yang model, which would be read-only. Now, what I want to do is interact with a topology. And I have a specific topology ID that I provide. In this case, it's the topology-netconf that I want to work with. Within that, I want to talk to a specific node or target a specific node. And in this case, in my example, I'm targeting VPP. And VPP is a software-based fast-forwarding engine, basically a fast switcher router that's defined completely in software, which I'll talk about a little bit more later on. So that was the URL, and now the body, this is what could be encoded in XML or in JSON. In this example, I'm using XML. And that information is dictated by this other Yang model, this network node topology. So what you can see here is that given a certain Yang model, it defines, it's easy to figure out exactly what your RESTCONF URL and payload would look like based on the Yang models that you're using and that are supported by your network device. So now kind of putting all that together, you can see that the key here is that the network device, which in this case is represented by this gray box, its configuration is defined by a set of Yang models, right? And we can interact with those Yang models using NETCONF, or we can interact with them using RESTCONF. And so we'll be using those models to set up different things in our network, like to configure BGP or QoS, or to create create a new VXLAN. So the important thing here is that regardless of how we talk to the device, it's going to be based on those Yang models. So in the example of a NETCONF client, let's say I was doing that, I would set up my SSH connection, I would encode my payload as described by the Yang model, I'd talk to the NETCONF server, which is running on my device, and I would interact with the configuration. Alternatively, I could use RESTCONF to do the same thing and even do these things interchanged. In that case, I'd be using HTTPS, but I'm still defining my payload based on the Yang models. Only now I also have the ability to use JSON in addition to XML. I then talk to the RESTCONF server, which would be running on my NETCONF device. And doing that, I'm able to interact with the exact same data store on my device. Okay, now the title of the talk mentioned network layer APIs. So far, we've still really been looking at device layer APIs. But we did that just to build up the way network programmability works. So now we're going to look a little bit at configuring things across the network. So in my example here, I'm again using OpenDaylight like I did in my previous example. I have 3 different network elements. A VPP, one instance of it, a second instance of it, and then a CSR1000v. And what I'm going to do is connect to each of those using OpenDaylight. Now the way I would do that, or a way I can do that, is by doing a post HTTP or RESTCONF request, a post through RESTCONF into OpenDaylight, and then OpenDaylight will take that and actually use NETCONF, which I've enabled on my OpenDaylight controller, to interface with each of these data elements. So what happens when I do that, and we'll look at each of these in a little bit more detail, but I want to show you the way the Yang models work in this case. So initially, when I make my RESTCONF request to talk to VPP1, what OpenDaylight does is it learns all of the Yang models that are supported by VPP1. It adds that VPP node into its inventory, and then also it takes those Yang models and adds them into its model cache. And when it does that, it actually can generate all of the code that it needs to interact with VPP1 based on those Yang models. So now it has the ability to interact with it. Even if it had never talked to VPP before, even if it had never seen these Yang models before, it can generate all that code on the fly to interact with it. So now I go and I want to do the same thing with VPP2. So establish a NetConf connection to it, learn all the Yang models that it supports. I add it into my node inventory. Now, I already know all of its Yang models, so I don't need to put them into my model cache, and I don't need to generate all the code for it, because I already know it. So nothing more is needed there. Now I go to the CSR1000v, establish a NetConf connection to it, again using SSH. I learn all of its Yang models. It has some of the same Yang models as VPP1 and 2, but there's some that are specific to it. So that means I have a few more models to add into my cache. I add the CSR1000v into my node inventory, and I add those new models into my cache and generate that extra bit of code that I need to work with those new models. So now dynamically, I've been able to discover these devices, and OpenDaylight's able to interact with all of them based on the Yang models that they supported. Okay, now we're going to go into a little bit more detail of exactly how that works. So in this case, it's the same scenario I talked about before. What I'm going to do is I'm going to use Postman as my application or my way of building out a RESTCONF request. I'm going to talk to OpenDaylight through RESTCONF, and I'm going to have it add, basically going to tell it to add this VPP element to its topology. So this is what it looks like. You can see here the URL that's been built up. This is the address of my OpenDaylight controller. I'm communicating to it using RESTCONF. I'm interacting with the configuration data store, which means it's read-writable, and working with the network topology to define this new node, VPP1. So once I do that, VPP gets added into its topology, and now with this next request, I'm asking for the NetConf topology to have it, OpenDaylight tell me what its topology is. And you can see that it's added this element, VPP1 is now added into its topology that wasn't there before. So this is what it looks like looking through the OpenDaylight CLI, UI. OpenDaylight has something called Yang Explorer, and that's, the Yang UI, and that's what I'm using here. You can see all the Yang models that are supported by OpenDaylight here. I'm going into this network topology model that we've been looking at, that Yang model, traversing down into it, and now I'm asking it, return to me the node called VPP1. Show me what you have about VPP1. You can see the RESTCONF request here that's built out, and when I query it, it echoes back to me, oh, you have VPP1, here its IP address, and a bunch of other information about it. So there I can see that I've added VPP into OpenDaylight. So the next step then is to do the same thing for the CSR1000v. Again, creating the right RESTCONF request using Postman and adding in the CSR1000v. So here's what it looks like in Postman. It looks a little bit differently just because in this case I'm making use of more variables, I guess, within my RESTCONF request. But still, it's the same idea. I'm doing a put to add a node. That node is the CSR. And here I'm actually showing what the body looks like of the information I'm passing in. And a lot of this is in variables that are defined elsewhere. But basically, I'm adding the CSR1000v into its topology. And then if I do a query of getting the NetConf topology, I get back that the CSR1000v has been added. So now both of these things are in my topology. So now the next thing I want to do is start to work a little bit higher level up, not just with the individual nodes, but to connect the two of them together, to create a link between those two. So now again, I would use Postman, and I would establish this link. And I'm running a little short on time, but let me show you what that would look like. So you can see here what I'm doing is a put, and I'm talking to the CSR, and I'm saying I want to configure a link from my Gigabit Ethernet 2 over to VPP, so establishing one side of the connection. So I do that put request, and then I just do almost exactly the same thing on VPP to connect it to the CSR1000v. And once I've done that, I have this connection set up. And again, I'm showing all this using Postman, so you can see the way that the requests are built, but you could very easily do the same thing with Python programmatically. So now you may say, okay, that's still not really a network level API, even though I'm creating a network by connecting two things together, because I'm still working with the individual devices. So the next thing then would be, for those of you who were here for the previous session, to take a look at something like MEF's LSO overall architecture and all the APIs behind it. And now you can imagine I can use those same APIs that are being defined there to interact with my network elements and configure not just a link between two routers or two switches, but actually to create a link across multiple service providers, and to do that all dynamically. And I'm not going to go into details of this in the interest of time, but rather just show you quickly what that might look like. In this example, I have 5 different service providers, and I want to establish a session to different endpoints that are reachable by different service providers here. So then the idea is I can go in and programmatically, by coming in through the Sonata API, which is the a service level API, I can make the right things happen on the network to set up those attachment points between all the elements that are needed. Here I'm doing it across 5 different service providers, just like I did it across VPP and the CSR1000v. It's basically doing the exact same thing, but just doing it more times and across more network elements. But it's all programmatic. So once you write the code to do it, you just run a little bit bigger loop, I guess, a for loop going through all those network elements, as opposed to just doing it with 2 of them. Okay, so to wrap up, SDN, it's more than just OpenFlow. Let me just finish this, and I'll get to your question. Network programmability is really, to me, the key benefit that we get through SDN. And the great thing about that is that it enables us to interact programmatically with the network. And then working individually with a device is part of the goodness of SDN and this network programmability, but you can realize even more potential, even more power if you're able to move to more of a network level APIs and do the type of use case I showed in that last slide of creating connections dynamically across a set of service providers. And then I just have some links, and the slides are all online too, and I'm happy to answer as many questions as I can before they kick me out.
So go back a couple slides.
Yeah.
So what? Okay. So
which one?
This one works.
Okay.
So on here, there's some vendors or service companies as well as service providers. How much of this is commercial? This would be really cool if it was commercial.
What do you mean, like commercially available?
Yeah. So if I ordered a circuit, would actually using the LSO infrastructure to speed up.
So far, I think it's only in like proof of concepts and that type of thing. I don't know if anyone's actually turned up an orderable service, because again, these things are in the process of being defined. I can tell you it was definitely done at, this particular one was done at MEF 17, so almost a year ago, as a proof of concept. So maybe it is an orderable service.
Okay, so this is proof of concept picture. Okay, gotcha. Okay, all right.
Yep. Any other questions? Okay, well, great. Thank you very much.